The next presentation is quite different from all the presentations you've watched so far. It's from Amit Sethi, professor at IIT Bombay. He'll be doing a technical presentation for explaining survival modeling for mortality risks and basic to advanced use of models. Amit Sethi is a professor at the Indian Institute of Technology, Bombay. His research group works on developing AI methods for analyzing medical data, especially images, genomics, and outcomes data. The research emphasis is on increasing the robustness and safety of AI models. Amit has a PhD from University of Illinois and Urbana-Champaign and a bachelor's degree from IIT Delhi. Please join me in inviting Dr. Amit Sethi on the stage.
How many of you wish you paid more attention to math when you were in school? I'm just kidding. So I'll talk about risk modeling. I will talk about survival modeling specifically. So my research group works on survival modeling for medical images. But the lessons that we have there are also applicable to insurance. So as the previous speaker was talking about his company, you all are very familiar that there are a lot of AI-based use cases that are now powering the insurance industry in various aspects. In the back end, at processing documents, processing claims, and so forth. But then also in underwriting and actuarial services. But at the core of actuarial services is predicting time to a certain event. So what do I mean by that? So basically, you want to predict risk, you want to manage a risk, right? And because of that, these are some of the works that someone in actuarial sciences would do, right? They would model events, time to events, such as not just adverse events like deaths, onset of disease, but also when a customer would churn, right? Or when they would file a claim, right? So these kind of things are crucial to your financial modeling because on top of it, you can add the risks and the value of the customer. So with that, you can you can quantify and manage your uncertainty. You can make premiums that are fair and sustainable, and etc. But in the end, you also want to be able to support compliance and be able to justify the decisions that you made for an individual. So this is at the core of survival modeling, right? So I'll skip this. So what exactly is survival modeling? So many of you might be familiar with these Kaplan-Meier curves, the survival curves. So today we are all alive, and in 100 years, none of us in this room will be alive. Sorry for the morbid fact. But so that survival probability keeps going down. However, for some people, it will go down faster, and for some, it will go down slower, right? So for example, those who might have healthy lifestyle, this might be lower and so forth. Those who have had, better history of managing their risk in the past, for that it will be better and so forth. But how do we model that, right? So we want to be able to stratify groups into different risk categories. We want to be able to rank who has a higher risk than someone else, right? But then our predictions also have to come with a calibrated understanding of the uncertainty, right? We cannot be too sure if we don't have enough information, for example. So typical survival modeling would work something like this. You would have a lot of historical data on which you would build your survival models. And in your historical data, what you see on the graph, that events start at a certain point, and then you keep, or like the observation starts at a certain point. So you are looking at a group of patients, for example, or a group of customers, and then you are tracking them over time. And then an event occurs at different times for different customers. But then some of them are also lost to follow up, in the sense that they dropped out of your policy, they stopped paying the premium and so forth. Now you have no information about that. So that is a critical challenge in utilizing a data which is called censored data. So your data is censored if you cannot observe the subject anymore. So survival modeling takes into account both uncensored and censored data, and it would try to build models based on that. And they're only useful if you can give it some inputs and it can tell you what the likelihood of survival is. So the workhorse model in this case is the Cox Proportional Hazard models. It's a simpler model. So you assume that this hazard function of how likely an event is to happen over time, that remains constant, but then you scale it up or down based on the risk factors. So it's a simple model, but it's very explainable in that sense. But now you have a lot of machine learning based survival models, right? And that is where a lot of exciting work is happening. Both exciting, but it's machine learning is also a double-edged sword, which I will talk about. Just because I work in machine learning, I don't think it's a silver bullet for everyone, right? We have to be careful where to use machine learning. So what does machine learning do? How is it different from Cox Proportional Hazards? So Cox Proportional Hazard, you can think of it as a simpler linear predictor type model. Whereas in machine learning, you can do more complex modeling such as nonlinear modeling. You can look at interaction of variables. So for example, if someone has a BRCA gene and BRCA1 gene and also smokes. So it's not additive risk, it might be multiplicative risk. Right? So these complex interactions you can model using machine learning models. So these are just a laundry list of different types of machine learning models, right? You can start from Cox Proportional Hazards, then accelerated failure time, which all you are familiar with, but then you can go into things like random forest, like tree-based models. You can even plug in deep neural networks these days to do survival modeling. What they do is they will try to model the likelihood of survival at different times using a complex model that can even take into account like any medical imaging that you might have done, any genomic test you might have done, complex panel of blood tests that you might have done. All those can be fit into machine learning models, provided you have enough data from the past to train these models. So in a nutshell, what this machine learning models do, if you have large data and you have people who can do machine learning with it, you will get higher accuracy predictions. That's a given. It will give you better accuracy than Cox Proportional Hazards or the risk tables and so forth, accelerated risk and so forth. However, the challenge here is that you need to have large amount of data. You cannot do this on, 100 cases or so. You need like thousands, 10,000s, lakhs of data, patients' data or subjects' data, and then you can produce highly accurate models. These will be like nonlinear models. They will model interactions between covariates better. They will handle censored data better, right? And if you have, let's say you have periodic tests and some of those tests are missed, they can also impute those things that you missed at different points for you. Okay? So that's basically the exciting part about machine learning. And you can give it any kind of data, provided you have enough data. You can give it genomic data, imaging data, blood test data, lifestyle data. Perhaps if you have an app and you look at the app usage or app location, that data itself, provided you have the permissions from the user to track that, you can use that in a machine learning model. So for example, in the US and some of the car insurance companies, what they're doing is they're tracking how fast the cars are going, how much they're accelerating, decelerating based on your phone data. And based on that, you can assess the risk of a person. So you can now answer questions like, what if suddenly now this patient went through a genomic test and BRCA1 gene was discovered? How much does that increase my risk? And does it help me with the financial planning because now I have aggregated information of many subjects, many customers in my database, new information that is coming in. Suddenly there's a craze that a lot of people are getting into fitness. They've started running marathons. How does that decrease your risk? Right? Can you now offload some of your investment and not have it in the pool that for the payouts, but you can actually do investments with that? If there's a customer who suddenly started becoming late in making your payments, does that increase your risk of default now? So these kind of things you can now easily do with machine learning models. But now all data that you feed into the model, it's not created equal. Some of this you can easily get, some of this you can cheaply get, some of it is expensive, and some of it may not even be ethical to get, or you may have a prohibitively high cost to get. So for example, what we will look at for whether I should use this data in the model is not only its predictive power, how better it predicts the outcomes, but also what is its cost and feasibility. And is it ethical and fair to use? Also, over time, can I assume that I will be able to measure this? Right? If you cannot measure it, then it's not of no use. What will be the quality of the data? Is it reliable? Will it be interpretable, stable over time, and so forth? Right? And does it meet my regulatory requirements? And once you have a model, it's not just the accuracy that matters. There are many, many things that you have to look at, right? So, for example, you have to look at whether it also gives you a good measure of its uncertainty, right? So, it may say that this event will occur in 10 years, but is it 10 plus minus 1 or 10 plus minus 5? Those are very different ways of looking at risk. Is it able to rank different customers, different individuals? Is it transparent? For example, complex machine learning models are not transparent. Cox Proportional Hazard model is very transparent. Is it robust? If I recorded some of the data, will the outcomes change very drastically? Is it fair, and does it allow me to have an action plan? So now I'll give you some examples from our medical research where we have done survival modeling. We have used imaging data, pathology data, genomics data, but we have also tried to make these models safer and more interpretable. So this is the first example where we looked at lymph nodes in breast cancer patients, and these lymph nodes don't have metastatic cancer. Yet, by looking at the architecture of the lymph nodes, we can predict which patient will survive longer versus shorter. Because if the cancer is more dangerous, it will change the lymph nodes, even if it has not infected it yet, even if it has not invaded it yet, it will change the architecture of the lymph nodes. So this is using deep neural networks and artificial intelligence. Similarly, we looked at 50 gene panel called PAM50 breast cancer, where we said that even if there's a cohort of patients, all of them have luminal A breast cancer, by looking at the heterogeneity of their genomic signature, we can predict which group is going to have a better survival outcome than the other. Then now, genomic data is expensive to get. Each test may be 10,000, 20,000 rupees. But pathology, if someone has gone to a clinic for suspected cancer, that pathology is very inexpensive to get. Within like 1,000, 3,000 rupees, you can get it. Now we have deep learning models that can actually look at the pathology and predict the same thing that a genomics did, which is whether there's heterogeneity in cancer, who will survive longer, who will not survive longer. And we can also, if you have from the past genomic data and pathology data, you can train models that will predict the genomic signature without needing the genomics in the future. It will just do that based on pathology alone. And it can compete with genomic models because it was earlier trained on data where both genomics and this pathology data was available. So all this prediction is fine, but what matters at the end of the day is not just the predictive accuracy. How do you measure predictive accuracy? Is that did you rank the patients well or not? But what also matters is that how much confidence do you have in your prediction? And is your confidence correctly placed or misplaced? So that's where uncertainty modeling comes in, where we use Bayesian neural networks to look at not only the survival curve that you see on the far right, but also the region of uncertainty around each prediction. So you may have, for certain measurements, for certain patients, you may have a particular prediction, but you may have high uncertainty around that. So you would model it very differently than those where you have a much better prediction. So this kind of brings me towards the end of the talk. So the take-home message here is that survival model is at the core of insurance industry, right? And when you use machine learning, you can increase the accuracy of your models because you can use more data, you can work with missing data, you can work with censored data, you can model complex interaction of variables and so forth. But accuracy isn't everything. So where to use a machine learning model and where to use a simpler model like a Cox Proportional Hazard models. That decision has to be taken at a business level by understanding where will I have to answer the compliance and where am I using internally just to manage my own risk. So those would be sort of like two different ways of looking at this. So in certain cases, if you want explainability and explainability, especially in accountability, you may want to go for a simpler model. But otherwise, if you just want accuracy for better planning, then machine learning models is definitely something to explore. Thank you.